Welcome everyone to our Distinguished AIR seminar. This week we're extremely happy to welcome Professor Kristen Grauman. As an introduction, Professor Grauman is at the Department of Computer Science at the University of Texas at Austin. And she's also a research scientist at Facebook AI Research, or FAIR. Her research is in computer vision, machine learning, and she's focusing on visual recognition, video, and embodied perception. Before joining UT Austin in 2007, she received her PhD at MIT, where we were actually office mates together. So I've known Kristen for a long time, and she's just an amazing researcher, extremely well-known, and is an IEEE Fellow, AAAI Fellow, Sloan Fellow, recipient of the 2013 Computers and Thought Award, among many other awards and distinctions. So I'm very excited to have Kristen Grauman. Please welcome her virtually, and I'll pass it on to you.
Great, thank you, Kate, and thank you very much for having me for this visit, and thanks you all for taking the time to be here. I am quite excited to share with you some of our recent work dealing with sound and vision, especially in 3D spaces. So this talk is going to be a mixed overview of kind of the general place we're going, some of the specifics of what we've done, and then a little bit of teasers on what we're doing to build from there. Okay, and I've tried to make this talk for a general audience because I know there'll be a lot of different expertise in this audience. So glad to talk about more details offline or by through our papers. All right, so to motivate kind of the big picture where we're thinking about perception problems that are closely linked with action. So this is computer vision, where we want to not just look at the world and understand it, but use our perception of the world to act in it. And that means both movement, so things like navigating, finding things, as well as manipulation. So being able to change the world, do things in it. And this has a variety of important applications that are making fantastic progress across the board in robotics and in augmented reality. Now, in particular, what I want to start with is thinking about agents that need to move around in environments that are unmapped. So this is visual navigation challenge, where you have an agent who's going to see an egocentric view, meaning whatever their first person camera reveals over time, and they'll be in some 3D space, and they'll have a navigation goal. And as we'll see shortly, that goal could be expressed in different ways. But the challenge is you want an agent that can be dropped in even into a new environment that isn't yet mapped out, and still be intelligent about moving as a function of what it sees in its camera. So you can think about our camera or our agent here being able to look at pictures like it's seeing there over time, and both flesh out its own map of the environment as it encounters new parts of it, as well as make good progress towards the navigation goal. And this is a really exciting problem, not without a long history, certainly on the robotics side and visual SLAM side. But what's really unique here is thinking about it as something that could be a learnable task. So being able to learn policies or behaviors for how to move around in a space, especially when the space is as yet unmapped or new to the agent. So our agents are going to see things like the video on the left. They may construct maps like I'm showing on the right, like a floor plan depicting where obstacles are and where free space is. And all the while, they'll be making decisions about how to move correctly to get to a given goal. Okay, and there's so much fantastic work going on in this space. I'm citing just a handful at the bottom here. And that's this new push to be able to learn, even in an end-to-end manner, how to perform in these new environments. However, there is a key thing missing that we'd like to address head on, and that's what this talk is about. These agents have been living in silent environments, and they are deaf. And so they're going about this task very heavily relying on their visual perception. So this work that I'm presenting today is about considering what we gain and how we gain it when we want to model
I don't know what that means.
sound.
If you like, I can search the web for Hey Siri, why do you game?
So
I don't know what that means.
Oh no.
Web form. Hey Siri, why do you game?
Siri got very excited.
I don't know what that means. If you like, I can search the web for.
All right, that's a new one. So my iPad is across the room, and Siri just tuned into my talk and had some not useful questions back. So anyway,
Yeah.
sorry for that. So speaking of sound in 3D spaces, we're looking to bring sound into 3D spaces and then think about how agents can leverage them for navigation and other tasks. So what do we get from sound? Certainly we can open up the chance to navigate to sounding objects. So think about the phone ringing in another room. We can understand activity. So activities often can have a signature sound associated with them that if we hear it and or see it, we'd be able to understand. Sound is also a kind of a fundamental cue about semantics. So imagine you're a robot at the bottom of this house and hearing some running water from the top right. This may indicate to you, though, perhaps the kitchen or bathroom is in that direction because of the semantics associated with that sound. And finally, sound itself is at the core a signal about the geometry and the materials of a space. Okay, so how the sound moves around and how we receive it would tell us something about those factors. So when we think about modeling sound for an embodied agent, there's going to be two key factors that are interacting to create the sound that we receive. So there's factors from the 3D environment itself. As I just mentioned, the geometry, the materials, as well as where is the sounding object and where is our agent. Those are all going to affect what kind of sounds we receive. On the other hand, we also have the factors attributable to the agent's embodiment itself. So if I take we humans as the agent, we have 2 ears. We receive what's called binaural sound, waveforms from to our right ear and our left ear. And so we'll specifically hear the spatial effects of audio because of things like the difference in time from when the sound hits the one ear versus the other ear, or the difference in its levels because our head is dampening the effect of the sound to the farther ear, as well as even, in our case, effects of the shape of our ears that will give us an enriched spatial element for the sound received. So the first piece of work then I want to show, kind of given that context, is our SoundSpaces environment that will allow audiovisual navigation in real-world scanned environments. So we can do these embodied AI investigations in a very reproducible and realistic way. Okay, so as I mentioned that there's been a lot of progress in developing 3D environments for embodied AI research, in which you have both the fast simulator, fast rendering, 3D assets like real-world scan environments and how they look from any particular angle that the agent might go to. And what we're adding here is the ability to also simulate sound in such a space. So we've done this for a family of environments. There are about 100 of them now. They are from the Matterport 3D and replica spaces, and they'll be real-world environments like the one you see over here. So we'll take those visually realistic 3D environments, and we've pre-computed audio renderings for acoustically realistic sounds, binaural sound that you can generate in real time for any sound of your choosing. So if you want to insert the dog barking, you would say where it should be barking, and then where your agent is at any moment in time would dictate what kind of sound you would read back from the environment. And we've done this by pre-computing what are called room impulse responses. So the function that says how the sound interacts with the 3D space, with the relative positions of the agent and the sound maker. So for example, if I was inserting at one of the places in this environment here, say the dog was to be placed here, then I can pull from any other position what is the binaural sound that would be received. Okay, and we pre-computed these room impulse responses using state-of-the-art bidirectional ray tracing algorithms in the acoustic domain. So what does this give you? Well, now you have the ability to work with these 3D environments and have agents that are no longer deaf. So I'll play you a short video here so you get a sense of what these environments look like, how the sound comes about to the agent, and how it changes over time as a function of the agent's motion. Now, keep in mind, to really experience this sound properly, you need to go right to our source video so that you could put in headphones and hear the left and right channel appropriately. But as it is, you'll be able to at least hear the strength of the audio as the agent moves. Okay, so you could hear hopefully the piano sound, the fire alarm beeping, and you could sense them getting louder as the agent got closer to the sources. And with headphones, you'll also hear the directionality of that sound as the agent moves. Now, that example also suggests the very first task we want to take with this new SoundSpaces platform, and that is audio-visual navigation. So we would like to have an agent who can find a sound source, even if that sound source is out of view. So the agent starts out here, say outside these two rooms, is looking for the phone that's ringing. And while from the onset it is not visible, of course, the sound is going to be the thing that helps to direct the agent to where to start to move. In this case, you can see sound bleeding out of the doorway of the proper room, and that would be a signal to start moving in that direction to navigate to the phone. This is in fact a new task in this domain to try and consider, and SoundSpaces is helping us accelerate progress on this task because of these acoustically realistic, visually realistic simulations. So a traditional task that you would pose for navigation is called point goal. And there's a lot of work looking at this. This is where the agent is told that, okay, your destination is at this delta X, delta Y relative to your current position, but you are in an unmapped space and you need to find it. This is still non-trivial because the direct vector to get there is not the correct path. There's going to be obstacles throughout, and the agent needs to learn and discover those obstacles as it goes. Now, in contrast, we're going to consider a task where the agent's not given the goal position, no delta X, delta Y, but it is told to find the sounding object. Okay, just like the phone example I was referring to. And we can consider a hybrid of these two, where the agent could be told the general direction of the goal, but also be listening in order to find it more efficiently. Okay, so we'll call these AudioGoal and audio point goal, respectively. Now, for the audio-visual navigation task, the first model that we explored is a reinforcement learning approach. So reinforcement learning, meaning we're going to have an agent train itself through experience to come up with a policy that tells it how it wants to move based on what it's currently seeing or has seen in the past, as well as what it's currently hearing or has heard in the past. And we'll start with a basic RL, reinforcement learning navigation framework, in which we have the inputs from vision, and we'll learn features from that with a convolutional neural network. But we also now have the features from the audio stream, which here are going to be represented as left and right ear spectrograms. And these spectrograms are encodings for the sound, saying the distribution of the frequencies of sound over time, and optionally some GPS sensing to allow the agent to do its own odometry in the environment. Now, these are all the inputs, and then from there, we have a recurrent network that's going to aggregate the history of these observations over time while learning a policy for sampling actions to take in the environment that are going to increase its reward. Now, the actions that'll be sampled will be things like turning left, turning right, going forward. And it's going to learn how to sample these actions well so that the agent can maximize a reward for getting to the target quickly. Okay, and after an iteration of this, the environment changes, which just means the agent sees something new after it moves. It hears something new as well, and this process will repeat. Now, something interesting we can do here is drop that reliance on GPS odometry, and I'll come back to that in just a couple of slides, where we can think of that audio goal setting where there is no geometric pointer to where the goal is. So first, let's think, how does audio help navigation? And let's see some initial results. So here's an example. You're looking at a top-down map where the agent can do the traditional point goal task. So top-down map, the white things are obstacles, the black things are free space, the gray things are observed free space. And here you have an agent that started at the blue position and needs to go to the yellow position. The best path to take would be that pink trajectory. The one the agent took in this particular episode is shown in blue. And you can see that by the time the episode ran out of time, the agent was still bumbling around at the wall of this upper room. And it's actually reasonable why it would do that. It has a strong incentive from the point goal task to move towards that goal. But there needs to be more intelligence to do it, which because it requires actually exiting that top room to carve a path down to the bottom. Okay, so when we consider this point goal agent, the success rates are in the numbers that you see here on the right, depending on the different modalities used. However, if we add the audio and consider the audio point goal task that I defined earlier, we see that there's some better performance. So the agent realizes that the sound's coming from that direction, but also hears it propagating through this space in a way that indicates which doorways would be good to exit or enter. And it does succeed in this case to get to the goal. And overall, it succeeds with pretty good margin over what you could do with the point goal agent. Okay, so we have agents then that are attuned to the sounds and using it to move towards the goals in the environment. And what's next to consider is to what extent is the geometry and direction information about the goal given to this agent through the audio able to overcome challenges it might face in terms of traditional odometry keeping. And in particular, as the GPS sensing gets noisier and noisier. And so that's what we're looking at here. On the y-axis, you have success rate of navigation. You want this to be high. And on the x, we're looking at GPS getting increasingly noisy, as it would and does in especially indoor environments. And you can see that the point goal agent we just looked at does suffer quite a bit once GPS is corrupted, right? It's no longer getting the right pointer to the goal, and that suffers. The audio point goal agent is more robust, right? There's still a pretty good rate of success, even as that GPS is starting to fall down. So that's encouraging. Now, perhaps even more exciting is if we pull out GPS altogether, we're left with that AudioGoal agent, the one that is navigating on its own to discover the goal position. And that by definition requires no GPS. So we'll have a flat curve here and a quite good, reasonably good navigation success rate. And you might wonder, well, what if sound gets noisy? Because this of course can happen too. And if we add noise to the microphone at a pretty healthy level, we're still seeing that these reinforcement learning policies can be reasonably robust to it. Okay, so I think this is an exciting result from this part of the work, suggesting how to move from agents that are being told where to go to agents that sense a dynamic sound event that they want to reach and discover exactly how to get there, even in an unmapped space. So here's just one example of the AudioGoal agent running, and it'll hear a phone ringing and move in this yet unmapped space. So the agent doesn't get this map on the right-hand side. It's discovering it as it goes. What it gets are the left two views and the sound. And we'll watch it go find this goal. So those red moments are collisions. It's getting stuck on an ottoman and then unstuck. Hearing the phone in another room. And finally traveling there. So you can see again, the shortest path would look like the one in the green. The one the agent discovered to take in this new environment is shown in blue. Now, another thing we can investigate is what about the environment has been learned from sound. And so what I'm showing you here are qualitative renderings in terms of T-SNE plots, 2D projections of the data coming from the learned CNN on top of those binaural spectrograms. So what did the agent learn about sound? What did it learn was useful to extract from those raw input sound files? And what I'm plotting here on the left is those points color-coded according to their distance to the goal. And on the right, color-coded according to the direction of the goal. So to the extent that these points cluster by color, it means that there's a sign of those features encoding for those properties. You can see it pretty strong in terms of distance to goal, where certain points from this encoding suggest that the goal is far and others would suggest it's close, and a more moderate but present encoding for the direction. And this is cool because we can certainly expose these parameters and even do analytically try to compute the direction of arrival of the sound and so on. But by not limiting to those factors, we're able to learn exactly what's needed from these spectrograms in order to achieve the navigation task. And what these plots suggest is that part of what falls out are those parameters about distance and angle to goal and other things that are useful to get to the target. Now, this model was the first attempt by us to bring sound into audiovisual navigation. Now, it certainly had plenty of ways to fail, and ones you could observe would be things like oscillating around an obstacle. We saw that with the ottoman, where it kind of got stuck a little bit and small motions, and then it finally got unstuck. Or certainly it could deviate from the very shortest path. So trying to build from the model I just showed, we're looking at ways to make this agent less myopic in terms of how it abstracts the action space. Okay, because you know this agent I just described was always making a decision about whether to move forward or turn, one step at a time. Another thing we could attribute some of these failures to is the simplistic memory, where we were using a recurrent neural network with a simple memory model to aggregate everything that was seen or heard before. So that brings me then to a next design for this model that we think will try to address those limitations. And there's two key ingredients. So the first thing we want to do is move away from that myopic action selection of always just thinking about the next motion. You know, albeit those motions were selected with a long-term reward of getting to the goal, but still at every time step, we were choosing one motion to make. So instead, what we'll introduce is the idea of audiovisual waypoints. You can think of these as sub-goals. So if you had the robot in this sketch over here and the phone ringing in a couple rooms over, then it may, desirable behavior may be that the agent sets sub-goals, for example, first to exit this first room, because the sound's not even in there, and then maybe to reach the door of another room, and so on. And so this would take us away from the myopic actions to sub-goal level actions about where to move next. And so the first part of the model will modularize the learning part and the planning part for this navigating agent in order to set sub-goals and then plan paths to them. Now, the other thing we were aware of as a shortcoming is the memory model. And so the second thing we want to introduce here is a more explicit mapping representation. So not restricting ourselves to these bottom elements as before of the egocentric view in RGB or the spectrograms, but now encoding a traditional occupancy map from the vision to say where obstacles were found, and new, an acoustic map. So a map that will record what sounds were heard as the agent moved in the space. Okay, so this will allow a more explicit encoding of the history of sound grounded in the space so that the agent can, we anticipate, learn a better policy for how to move towards a goal. Okay, so two main elements, the waypoints and this multimodal spatial memory. And if I put those ingredients in with a model like the one we saw before, then it gets enhanced in this way. So now we still have visual inputs coming in, but now we'll make this explicit ground plane map of where we've detected free space so far. We'll still have those audio spectrograms coming in, but now we'll keep not only a binaural CNN encoding, but also this acoustic memory recording the intensity of audio experienced at every position the agent visited. And then we'll continue with this recurrent model as before, but now its action space is not turn left, turn right, move forward, but instead is to sample a waypoint. So it'll sample a delta X, delta Y that it decides it wants to move to. Think of that as, the next doorway, perhaps, or the point beyond the couch that it can't see. These will be automatically generated by the policy itself. And then the agent will plan a path in this separate module on the right-hand side to get to each of those sub-goals. Then as before, the environment changes the observations because we've moved, and this process will continue. And meanwhile, during training, we're rewarding agents that reach the goal efficiently. Okay, so what's new about this model is both the multimodal memory that's being encoded, as well as this idea of directly learning to set waypoints. So in other navigation work, you might set a waypoint according to looking at the farthest points on the frontier of observed space, or even supervise models or heuristics to set these sub-goals. Whereas what's new in this framework, even outside of the audiovisual aspect, is using the policy to learn directly to set these waypoints. All right, so let me show you an agent at work here. Similar visualizations as before, egocentric view on the left, floor plan on the right. Agent is this arrow. And what you'll see are yellow points that are waypoints, the agent setting for itself over time. And the purple trail of points that you'll see will be the acoustic memory plotted out here on the floor plan. So here again, it's going to be looking for a sounding object, the goal, which is the red square in the bottom left. So it set another waypoint, the yellow dot. It reaches it by planning, sets a new waypoint, which is a doorway. Reaches it. We get closer and closer to the goal, and I'm sure you heard it getting louder. Meanwhile, that trail of the purple dots is recording for the agent where it experienced the different sounds, allowing it to think ahead more fully in order to set intelligent waypoints and then get to the sounding object. Okay, so back to evaluation then. Now we've made these improvements to the model, and we can look at the performance on AudioGoal as before. Here's an array of metrics. We could just concentrate on the first column, which is the success rate normalized by the path length. So you want to have the agent succeed in finding the goal and also do it as close to the shortest path that exists as possible. And what we're showing here are some varieties of our method on the bottom, AV1, which is audiovisual waypoint navigation. And I'm also showing you what we could get before here in the blue row, with the simpler models, with the simpler memory and the lack of these waypoints, as well as some concurrent work with that previous model that is shown in green that would use audio and vision in somewhat separate ways. So it would predict where is the goal first, given the sound, and then plan using the visual input to a path to get there. And so these results highlight both the value of adding the waypoints in memory, as well as the value of learning in concert between the audio and visual signals throughout the entire navigation experience. So far I've talked about navigation using sound, and next I want to highlight in shorter form some of our even more recent attempts to bring in some of these other elements like semantics and geometry and materials. And so first, let's talk about the semantics. And this is very much in the context of the AV navigation I was just describing. But the main step forward we want to take is to both enhance the platform and the task. So the platform side, we want to have objects that sound and appear. So in other words, rather than the phone being placed in an arbitrary position in one of these environments, we would have phones that look like phones and make phone sounds, and dishes that look like dishes in the kitchen and make dishwashing sounds, and so on. So we're going to attach in the simulator meaningful semantic sounds to meaningful semantic objects. And this will be, on the platform side, and it means the agent will be, on the flip side, able to start to learn connections between the visual objects and the sounds that they make through its own interaction with the environment. On the task side, we are going to increase the difficulty in a couple ways. One is these will be sounding objects that don't sound repeatedly. So they may sound for a bit and then they're quiet, and yet the agent still wants to find them. Furthermore, they may be sporadic sounds, right? So they may come and go over time. And so without getting into the modeling details here, I'll first show you an example of these semantically meaningful sounds placed in a Matterport environment with SoundSpaces. And so this first one is going to be a drawer opening and closing. Okay, and it's ceased to make sound, but this was the location of that sounding object. The next one, you'll hear a sound coming from the bathroom. And there's a toilet. There is a toilet sound. So now these are starting to match up, both what the objects look like and how they sound. And furthermore, I won't go into detail for time, but we've also introduced a model that learns to infer both the object category and location, and maintain a memory that can handle these brief sounds. Okay, so this allows us to move from objects placed in the world that we navigate to outside of their visual context to semantically grounded objects in the space and short-lived sounds. The next bit I wanted to briefly preview is looking more at the geometric aspect of using the audio and visual streams here to do floor plan reconstruction. And this is really cool, I think. So the goal is you have a short video and you want to infer the layout of the entire home, the entire space. So, with enough observations, with an exhaustive search and video through an entire house, we should hope that we could reconstruct its geometry and we could get its floor plan. But here, in contrast, we want to do this explicitly when the video is very short and it's not exhaustive throughout the entire home. So imagine on the left, if you had a video sequence comprised of those viewing cones, there's 5 of them shown. Now, if you were to strictly map using what you could see, you would cover regions like the ones that are shown in full color here. Right, and you could do usual things like looking at depth maps, projecting to the ground plane, finding where all the obstacles in free space are. However, if this agent takes the video and not just looks at the pixels, but also hears the sounds, we hypothesize that it can have a much fuller estimate of the layout of this space. And it'll come from a couple factors. One, the pure geometry of the space is reflected in the sound. So the way in which the agent receives multi-channel audio with the sound bouncing around from different surfaces, even those behind it or out of view of the camera, it can get some spatial signal with which to learn to create the map. And then up a level at the semantic side, we know that there will be different objects associated with different types of rooms that would hint at what lies beyond walls or behind the agent's camera. So for example, our agent here with the blue camera motion might hear some kitchen-like sounds coming from the left, and without glancing there or walking into that space, can start to anticipate not only the size and layout of the room, but also perhaps its type. And so that's our idea, to go from short videos to extract the map of the environment. So we'll call an interior map, this occupancy map on the top, as well as a semantic room label map that says which rooms are where: kitchen, bathroom, family room, etc. Okay, and so the key ingredient will be to try and learn how to make these structured output predictions using both the vision and the sound. And again, as before, for time, I'm not going into the details of the modeling, but more hoping to give you an idea of the problem itself and the approach or the kind of results we can get. The approach we take is going to think of it as an encoder decoder that's going to look at the sequence of these images and sounds over time and learn in a supervised way to decode back out to a ground plane map that says where the free space or occupied space is. So here's just one example, a static one, where I'm showing again the camera trajectory with these cones. So there's a handful of camera positions, and the green overlay that you see here in 3D on the left or in the top view on the ground plane on the top right, these are the positions that the agent predicts are free space. And you'll notice that plenty of them are behind the camera and were never glimpsed by the camera's field of view. But they can be estimated when we use this audio-visual floor plan approach to both listen and look at what's around. Now, to contrast that, if you were to solely look at what's absolutely visible, meaning just doing the geometry from the input vision to project to the ground plane, you would get on the left-hand side the cyan region as free space, which is much more limited view of this environment because it doesn't have the benefit of sound. Furthermore, as our results in the paper show, if we compare against a state-of-the-art vision and vision navigation mapping method that does do some extrapolation according to the visual channel, it'll still fall short without the ability to hear these sounds. Okay, so now I want to show you a video example of the agent constructing over time the audio-visual floor plan using this multimodal sensing. And so you'll hear some familiar object sounds. This is what the agent's hearing as it moves. And as before, they get louder and they move as they're supposed to, but also they help flesh out where the free space sits in this environment. So here's one example. Starting to expand its map estimate on the right-hand side. Okay, so you could hear some household noises. So these are just passively sensed sounds that the agent receives, and then it knows how to map those based on the properties of the raw audio, and not shown here based on their semantic room types, in order to flesh out this floor plane map on the right-hand side. Here's a second example with just some different sounds, where again, you're going to watch for this green map to expand, and the more it expands correctly with a small amount of video frames, the better this approach is doing. And then at the end, we'll contrast that with what it can see if only paying attention to the visual cues, and that'll be the smaller cyan map. Okay, so you can see the much broader map made possible by using audiovisual sensing, and the much smaller map if we were to restrict ourselves to traditional visual map. All right, so we have talked about finding things in a space, even when we can't initially see them using sound, as well as leveraging their semantics associated with different room types in order to build maps of an environment. And then the final piece I want to look at is coming back to the raw geometry and the materials of the space as revealed to us through the sounds. And here I'm going to keep very much in that theme, but now we're going to think about agents that are not navigating, but are instead learning representations through their interaction in the space. Okay, and the approach I'm about to introduce is called VisualEchoes. And an important thing to note about what we do in this stage is that, before we've been thinking about sounds in the environment being issued to the agent and the agent reacting accordingly. And so that was where a goal was making a sound and the agent would move to it. Now let's flip this and think about the agent emitting a sound and then listening to the response from the environment, or in other words, the echoes. So this will be what we'll show is this will be a way for the agent to gain a richer visual encoding for its environment if it understands how the visual surroundings relate to the echoes it receives during training. And to help motivate my story here, we can draw on an old movie called Daredevil, in which there's a character who can not hear, but cannot see, but can see by listening. And so the character is going to hit this gate and then see the shape of the scene based on the echoes that come back. Okay, so our agents won't be nearly as dramatic, but we can take inspiration from this basic ability to sense space through the reaction of sound. Okay, and this is the core idea then. We want to learn an image representation through echolocation. And we're treating this, again, not in the specific case of navigation, but instead in a feature learning domain. So the idea is to learn good features that will benefit hopefully many downstream tasks. And unlike before, I'm going to consider a case where at training we have both images and sound, but at testing we can only assume images. Okay, and that's also different from what I've shown before. Now, the array of tasks that we'll be targeting are all sharing elements of spatial reasoning. So we're going to look at depth prediction, surface normal estimation, and visual navigation. So the key insight of the approach we want to pursue here is that agents can learn from their environment by interacting with it, and specifically, in our case, interacting it with it from an acoustic standpoint. Okay, so a feature learning, a self-supervised feature learning approach in which the agent gets better at its own perception because it starts to understand the link between what it's going to hear and what it's going to see. All right, so let me say some more about how we actually do this. So in SoundSpaces, we can, as you recall, create or generate the visual and audio observations as we please as a function of object pose. So if I took a 3D environment like the one on the left, and then sample an egocentric view from RGB and depth, I can also sample the egocentric audio in terms of, as before, left and right audio spectrograms. Okay, and those will be associated with a given camera pose in the environment, but we can change that pose. So imagine even at the same position, rotating this camera and generating the same series of observations. So now you know for some given position, how things look and how they sound if I face a different way. Okay, so this is unsupervised in the sense that this just requires an agent to be in the world and take motions to observe new things. Now, to get to the final point that I was trying to describe a moment ago, first we want to check, is depth something that will be predictable from the echoes? Or do echoes help estimate depth? We already know a great array of techniques in the vision literature that can take single view RGB photos and learn to estimate the depth that goes with them. The question is, what will echoes do to enhance that? And these samples start to show what it might do. So here you have an RGB photo on the left. The true depth map is the second column. And here, red means far away and dark blue means close. And with RGB, you can get an estimate of that shape of that scene. If you use even just the echoes by themselves, there is a good broad stroke about the shape of this scene. And if you put them together, they actually get a bit better. So in this case, look at the top where there's a protrusion of the back wall, but it's not that large. Now it fools RGB because it looks like a strong edge. That might mean a very different depth rating, but it doesn't fool once we add the sound. So that's just an anecdotal example of how they might work together in a complementary way. But across the board, we are seeing that if you train a convolutional neural network to estimate depth from RGB or RGB with echoes, you can do better once you've added that sound. Okay, so echoes inform us for depth perception. Good, we're expecting to see this, and it's good it comes out from this data. Now, finally, let's put the method in place for visual echoes. So we want to learn a visual representation, and the key idea that we pursue here is that we can self-supervise this task based on the congruence or the incongruence of an echo and a view. Okay, so there'll be a stream for the visual as before, what the agent sees in front of it, and we'll be learning some encoder for that stream. Then we have a stream for the audio as before, and we'll be learning for that stream as well. But here's the task. During training, the echo that's provided in pair with the agent's RGB view is going to be either the correct echoes, the ones that the agent would hear if emitting sound in that environment, looking in that direction, or the wrong one. So we'll let the wrong ones be the echoes it would hear if facing a different way, to the right, behind, or to the left. Okay. And so with these pairings then, the job of this network is to predict from both the audio and visual cues, what is the orientation of the received echoes? Now, if you can train a model to do this well, it means that from the visual stream, it needs to be extracted whether there's consistency with the sounds, the multi-channel sounds that are showing the geometry of the scene with the geometry of the scene as observable in the pixels. And if we can tell their consistency and furthermore even classify the orientation offset, then we're able to pick that up from the visual stream. So that's the main idea. And so this is a self-supervised way to learn features from echoes. And what we really want out of this is the visual encoder. So I mentioned before, at test time, we can assume no audio, suppose, but we still want to satisfy these visual tasks. And what we can show is that by embedding the audio during training only, the encoding is enriched and we can perform better on those tasks. So for example, coming back to depth prediction, if we take it on a real world image test set, a popular one for this task, NYU, then we can see that we're enhancing the depth predictions over what a model trained from scratch would do. So this visual encoder is enhancing learning for depth. And you can look at this as a first step for us, example, going from sim to real, because we did train this encoder through simulation with SoundSpaces, with Matterport, but here we're testing it on real images that were disconnected from those environments. And in fact, we've looked not only at depth, as I mentioned, and shown that this has a accelerated learning or even improved accuracy of learning compared to traditional supervised pre-training or learning from scratch, meaning without this echolocation self-training step. Also for surface normal estimation and visual navigation. Okay, so the main message with these results is that we can be competitive with the supervised pre-training and sometimes even better than, given the closeness of this echolocation task, which is itself very much driven by geometry and the geometric and spatial nature of the visual tasks we're trying to solve here. Okay, so I'm going to close the talk here. I've shown ways in which we're exploring how to achieve spatial understanding from audiovisual observations. This included introducing SoundSpaces, a public platform that you can use now for audiovisual rendering for agents that move in a space. We started tackling the challenges of AudioGoal and Semantic AudioGoal and putting forth some models to do it. By the way, we're also hosting a challenge at CVPR this summer for other agents to compete on this new AV task. I introduced models based on waypoints and acoustic memory. And then I showed a little bit about floor plan reconstruction and a self-supervised feature learning using VisualEchoes. The next things that we're attempting include furthering the approach for sim to real transfer. So we could learn these policies for how to move over in simulation and then bring them out on a real robot in our lab. Also interested in looking at multi-agent or even adversarial settings for these agents that understand other sounding objects. And finally, we're continuing to look at tasks beyond navigation, such as being able to hear and separate sounds in a 3D environment based on how we move. Okay, so I'll stop there and be very glad to have any comments or questions.
Thank you. I'm providing a sound a substitute for the applause that we would have in normal times. That was a great talk. Thank you so much. Yeah, so if there are any questions, please put them into the Q&A and I will moderate. So I will look at them and read them out. So while we're waiting for the first question, oh, we didn't have to wait long. So we have a question from Carly who says, hi, Kristen, very interesting research. Did you also test how noise affects echolocation? I imagine having music, etc., in the background might make it hard. Yeah, I actually had this question myself.
Yeah, so for the VisualEchoes, I think not specifically, but throughout the navigation, yes. I didn't show it here, but we do experiments with what we call distractors. So, you know, you've got the phone ringing, but you've also got the AC running or music elsewhere in the scene. And this is important for sure for real world tests to be able to see, can you learn to decipher not just where the sounding thing is, but the one that you're interested in relative to any of these distractors. So yeah, that's definitely something of interest. And the encouraging output so far is that this can be wrapped into the policy learning. And so in having trained with distractor sounds, then the agent can pick up the ability to isolate the one of interest to perform the navigation task.
One of the things that I kept thinking when you were describing all these agents moving around and following sounds and achieving a goal is some scenario where you could just you know, if Siri or some agent could move around and you could just call it to come to you.
Mm-hmm.
Right, that seems like a fairly a useful feature. You know, if you have a robot in your home, rather than kind of using an app or something or looking for it, you could just call out its name and it will come. I don't know if you ever think of that, or if that would be do you think that would be any different than using these repeating sounds?
Mm-hmm.
But instead of having that kind of repeating sound, have a human call the agent's name and have the agent be able, I guess that would be a harder.
Yeah, it's very related actually. And we are looking at this and specifically for speech targets. So the job becomes, like you said, so it would be a non-periodic sound, and that is already present in the semantic audio goal where the sound can drop off even though you're still in charge of navigating to it. But some work that I haven't shown here, but that we've done recently is to move to here. So there's some speaker and some other cluttery or background or distracting sounds in the environment. And the speaker, think of that as, just as you're saying, you know, that maybe the person's calling for the agent. But it won't be clear either what they're saying or where they are until the agent takes some motions. And so it is still an audio navigation task, but now with speech that's amidst other household sounds and for an unknown and for an unknown position. And here, the way we've tackled it is that you could train the agent to navigate to the sound. That's very much in line with what we showed here, but also we're interested in training it to separate what's being said. So maybe the robot doesn't need to come all the way to where you are to get your request in the home, but it should get to a position where that request is clear, right? So whether you were asking for ABC or XYZ, the agent would position itself so that the speech and the language was clear enough to get that signal.
Yeah, I guess another application I just thought of is detecting falls by sound and, you know, coming to the rescue potentially. Yeah.
It's a great example. I mean, when events happen out of sight, we still want to know that they existed or what we might want to do about them. Yeah.
Right. Okay, great. So we have another question from Vitali. Vitali says, thanks for a great talk. In the vision domain, Lambertian surfaces are generally well behaved, while occlusions tend to complicate our algorithms. What are the corresponding simplifying or complicating factors in the audio domain? Thanks.
Yeah. So yeah, I mean, on the simulation front, there's the level of precision of the simulations generating, in our case, these room impulse responses. For example, how many bounces do you let the sounds go through before you truncate, and how many are captured, or how many channels of the audio are simulated. And so those are decisions that would affect, or you can think of these as assumptions about how faithful the simulated sound is with respect to real world sound. And those are known dimensions to trade off. Others that we might encounter in the kind of work we're doing, like on top of that, I think relate to, if you jump up a level, things like how much do we assume clean sound sources, how much do we assume the distractors exist or don't exist, and that's some of the experimentation is about testing just that. Similarly, you can think of, just as a parallel from the visual side, often we would think, well, what if there's noise in my pose estimation for my agent, whether extracted through GPS or extracted through visual odometry. Similarly, you can, as one of the results hinted at, we can think of microphone noise. So we have environment noise in terms of distracting sounds that aren't part of the puzzle, but are still audible. And then we have sensor noise in terms of the microphone and what it's receiving versus the true sound in the world. So I think those are a handful of examples of ways in which you can, on the simulator side, make decisions about the precision of the sounds that will be provided. And then on the task side, decisions about or assumptions about what's known in the scope of the problem.
Yeah, that's interesting. We have another question from Vidya. Vidya says, thanks so much for this talk. Could you explain the waypoints a little further? I'm not sure I understand the difference between calculating those and calculating the next step in the original version of this model.
Yeah, thanks for the question. So the original version, so in any of these RL policies, you have the action space, which is the thing the agent has signed up to do. So at every step in the first model, we could say, agent, turn left, right, or go forward, 1 unit. In the second one, we can say, agent, go to delta X, delta Y. And that can be, to some limit far away from the agent. And so the distinction then between the two models is the first one is every step within the RL paradigm. And then in the second model, we've brought in a mixture of learning and planning. So once the action of moving to delta X, delta Y is chosen, which that is the waypoint or the sub goal, the agent kicks into planning mode, and given whatever map it has so far, will compute the shortest path to get to that target position and either succeed or fail, but then return control to the learning. Okay, so that's the difference. It's kind of the granularity of the action space. And in principle, the second model has the freedom to choose that granularity, right? Because it doesn't have to be one step, but it could, it could always convert to say, well, the next action is to just go 1 left. But it's also free to set a further sub goal that would take it, in my cartoon examples, things like taking it to a doorway in a single action choice.
Great. Margaret has a question. What about recognizing changing environments? The sound of chairs being moved, doors slammed.
Yeah, this is so important. And so far we can do this on the sound side, but because we work in simulation, for learning anyhow, not on the visual side. But this is coming, not by work from my group, but for example, work in the Habitat project at FAIR, where there's starting to be at least the ability to insert dynamic objects. So you could have the environment change visually over time, not just orally. And in some other kinds of work, interactive environments where drawers can open and look different than when they were just closed. So we haven't achieved that mix yet in terms of the sound, the dynamic sounds with dynamic objects, but we have done the dynamic sounds. And so I do think this is, a great thing to pursue. And never mind the real world, you get this for free, right? I mean, these things just happen, but to be able to kind of push on this reproducible and large scale training advantages that we get from the simulation world, we're not yet there at that level of simulation for dynamic visuals.
Yeah, simulation is hard. It's a hard problem in itself. So maybe we'll take one last question here from Sid. Thanks for the cool talk. Curious, have you looked into agents making sounds of their own, like sonar, to use that to improve mapping? I'm assuming focusing on specific sounds as opposed to arbitrary sounds could probably help improve predictability.
Yeah, definitely. So the VisualEchoes is a first step in that direction, where the sounds are being emitted by the agent in order to gain representation. But I do think there's important ways you could extend this. I mean, one, I think your question alludes to, which is the selection of which sound to emit, given the conditions, right? So maybe we can be intelligent not only about what we learn from the sound and the vision connection, but which sounds issued at which moments in time would be most valuable. And there's also like a sense of kind of active, interactive learning that you could think about there. And it applies, in our case, it was kind of a tool towards feature learning for images, but similarly can be explored for mapping or maybe directly for navigation. So the agent that hears stuff in the world, fine, but also who maybe wants to find a visual target, but is using sound or intelligently emitted sound in order to map to get there faster.
Okay, great. So with that, we'll wrap up. Thanks again very much for the talk. Thank you to all the attendees. And yeah, we'll close. Thank you. We really enjoyed having you.
All right, thank you, Kate. Thanks, everyone. It's great to be with you today.